Alright, let me start with a question that might just blow your mind. What if reality itself, everything you see, touch, and experience, isn't smooth and continuous, but instead made of tiny, fundamental pixels of space? Now, I know that sounds completely science fiction, but stick with me, because this is where deep, cutting-edge physics meets a concept you likely encounter every day on your phone screen: resolution. Except, we're talking about the resolution of the universe itself. Yes, the idea we're exploring today is that reality itself might be quantized, packaged into blocks so tiny that they make the very idea of an atom look gigantic. It all comes down to the Planck length, which is, in essence, the smallest scale at which the laws of physics as we know them might even make sense. Alright, so let me set the stage here. In our modern theories of physics, we've got these two juggernauts describing reality in drastically different ways. I'm sure you've heard of them: general relativity and quantum mechanics. General relativity rules the big stuff: gravity, black holes, and galaxies doing their cosmic ballet. Quantum mechanics, on the other hand, operates the microscopic, the subatomic, where particles dance around in ways that can only be described as, well, bizarre. But here's the catch. The two don't quite play nicely with each other when pushed to their extremes. And at the very crux of their disagreement, we find this legally mind-blowing quantity called the Planck length. But what exactly is it? Let's get to that. So the Planck length emerges when you combine three fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. Without diving into too much math, it gives us a result that's unimaginably tiny, about 1.62 times 10 to the negative 35 meters. Now, to make that even remotely comprehensible, if you blew up a single hydrogen atom to the size of the observable universe, the Planck length would still be the size of a single atom relative to that scale. It's that small. You could line up about 10 to the 35th Planck length side by side just to span a single meter. And here's where things start getting deeply weird. Okay, so far, we understand that the Planck length is incredibly tiny. But why does it matter? What does it tell us about reality? Well, here's the deal. Physics, at its core, is about testing limits. And when we consider distances smaller than the Planck length, the math starts to break down. Our equations from relativity and quantum mechanics literally stop working. Space itself turns into a frothing chaos, a foam of space-time instability that no longer has any classical meaning. In essence, it tells us that we can't meaningfully talk about or describe distances smaller than this scale. It's almost like the cosmos has a built-in resolution limit. Now think about that for a second. At larger, everyday scales, we experience the world as smooth and continuous, like a perfect analog movie. But at the quantum level, it might actually be more like a digital photograph, made up of discrete, indivisible bits of space-time. And this raises a tantalizing question. Are we simply bumping up against errors in our models of physics? Or is the quantization of space an indication of something fundamental about the nature of reality? To answer this, physicists have turned to something called quantum gravity theories. Now hold on. Don't let that term scare you off. Let me break it down simply. One of the gnarliest problems in physics is trying to unify general relativity and quantum mechanics into a single coherent theory, something that works at both the scale of black holes and subatomic particles. The Planck length is like a warning sign that says, "Here be dragons." It's the frontier where our current maps of reality make no sense, and the clues we need to solve this problem might be hiding within its limits. Let's dive deeper. One of the most promising candidates for a theory of quantum gravity is something called string theory. According to string theory, the most fundamental building blocks of our universe aren't particles, but tiny, vibrating strings whose harmonies dictate the various forces and particles we observe. And here's the kicker. Those strings are thought to be Planck length in size. That's their fundamental scale of existence. Every electron, quark, photon, the whole zoo of particles, could just be different vibrations of these unimaginably small strings playing their cosmic tune. It's through this framework that the granularity of space-time starts making a bit more sense. But of course, string theory isn't the only game in town. Loop quantum gravity, another major contender for a theory of everything, takes a different road to the same destination. Imagine space-time as a kind of quantum mesh or lattice, woven together by discrete chunks of space and time at, you guessed it, Planck length scales. Philosophically, it would mean that space isn't the infinite, smooth expanse we've always assumed it to be, but rather a finite fabric of elementary patches, woven tightly together, almost like pixels on a screen. Now, here's where things take an even more peculiar twist. If space-time is quantized, as these theories suggest, then our very concepts of distance, time, and motion might need a fundamental overhaul. Think of it like a video game. In a virtual world, you can move characters smoothly on a screen, but under the hood, it's all discrete jumps between one pixel and the next. Could it be that our universe works like a highly complex simulation, where even the smallest scales of reality are coded into something finite? Some researchers have even proposed that strange physical phenomena, such as the energy density of the vacuum or the so-called holographic principle, might be pointing us toward the same conclusion. The idea is that space-time might store and process information similarly to how a computer does, with the Planck scale acting as the raw code. But as enticing as these speculations are, we have to remind ourselves, we don't yet have direct evidence that space-time is discretized. All we've got are elaborate theories trying to fill in the holes. And those holes, by the way, are where the debates happen. For example, critics of these approaches point out that many quantum gravity theories haven't yet made predictions we can test experimentally. It's one thing to claim space-time might be quantized. It's another to actually measure it. Other researchers argue that there's no good reason to bias physical theories toward discreteness over other possibilities, like continuous but probabilistic models at small scales. And then you even have quantum field theory diehards insisting that, until there's reason to discard classical spacetime, we should just keep improving our current models. All these positions highlight that we're still riding the edge of what's knowable right now. But let's zoom out a bit. Let's take a wider lens to understand the beauty of this conversation. Whether or not the Planck length is an intrinsic limit of nature, it serves as a stark reminder of the gaps in our understanding of the universe. And that missing understanding touches on questions that go beyond physics. Is there a smallest unit of reality? What does it mean if the universe has a finite resolution? And more profoundly, if there are limits to observable spacetime, what does it say about our place as creatures trying to comprehend the infinite? To me, the Planck length is humbling in the best possible way. It challenges us to question assumptions we didn't even know we were making, like whether space itself is infinite and seamless, or if it's something less classical, more quantum, and far stranger. It's that kind of curiosity and skepticism that keeps pushing humanity forward, step by hard-earned step, into the unknown. And that, folks, is where we'll leave it today. Now, I know this was a heady topic, but I hope it fueled your inner flame of curiosity, just as it does mine. If you enjoyed this deep dive into the universe's smallest scales, consider giving this video a like and leaving your thoughts in the comments. What fascinates or frustrates you most about the Planck length? Have theories like these changed how you see the world? I'd love to hear your take. And don't forget to subscribe to Hyperfocus. I've got plenty more where this came from. Thank you for watching today. Stay hyper-focused and let reality's pixels keep you wondering.